We will continue with our discussion of rotor in forward flight. In the previous few presentations, we looked at the rotor force balance, how the thrust it has to be tilted forward, not only to uphold the weight upwards, but also to provide the propulsive force forward. Then we talked about how much inflow does it take. We extended the actuated disc model that Rankine had developed for rotors in hover and vertical climb to forward flight in a phenomenological hand-waving model. So this was what was done by Glovert. So we came up with an inflow model called the Glovert's inflow model. So we found that the induced velocity is a nonlinear function of the thrust coefficient or the thrust. Alpha tip path plane, the angle that the tip path or the rotor disc makes with the oncoming free stream, and also other factors such as the forward velocity V infinity and a disk area A and the density of operation rho. We also came up with a non-dimensional expression for lambda I, which is the induced velocity divided by the tip speed, omega capital R, in terms of Ct and advance ratio mu and alpha tip path plane. So these were all developed in our previous videos. Now we come to a question of how much power does it take just for the rotor, not the whole vehicle, to move in forward flight. What happens? We will add the vehicle component a little bit later in this module or in this video. So let's look at that. So what happens is this is the rotor disc. We have done it as so it's horizontally. Free stream is coming at an angle. So the angle between this orange line and this rotor disc is alpha tip path plane. Therefore, the parallel component of this free stream is called V infinity cosine alpha tip path plane. The vertical component is V infinity times sine alpha tip path plane. So the free stream component is always shown as an orange velocity. As we discussed earlier, the induced velocity is zero, very far above the rotor disc, just like in a Rankine disk model. But by the time you reach the rotor disc, induced velocity has already reached a magnitude of v perpendicular to the rotor disc. Then by the time we reach the far wake, it has doubled to quantity of 2v. So what has happened is the total velocity vector is getting longer and longer. That means the kinetic energy per unit mass, which is 1/2 rho times this pink line squared, is much higher than the kinetic energy of this orange line that we started with. So we're coming up with a certain amount of energy. We are leaving with a lot more energy. So where did this energy come from? This energy was added by the rotor disc. So the rotor disc does work on the fluid. So per unit mass, we know the energy is 1/2 of velocity squared. So we need to take the mass flow rate, which is mass flow per unit time, times kinetic energy out minus kinetic energy in. That would be the power expended by the rotor, purely from an induced power perspective. We are only talking about the induced velocity, not about skin friction, not about friction drag or anything else like that. So let's make this a little bit more clearer. So way up here, the velocity is V infinity. So the energy flowing in is 1/2 times mass flow rate times V infinity squared. This has got a per unit time. So it's the energy per unit time. So this has got a units of power that is flowing in at this rate. By the time you reach here, this orange line has elongated to become the pink line. So it's got a horizontal component V infinity cosine alpha tip path plane that does not change. The vertical component of the orange line is V infinity times sine alpha tip path plane that did not change. But what has changed is we have added this extra induced velocity here, which was not present up here. So the energy flowing out is 1/2 times the mass flow rate times this square. So if you do the algebra, expand this, then cosine squared plus sine squared theta alpha tip path plane is 1. Then we get this number, this number, this number. So if you take the difference between how much energy is flowing out per unit time and how much energy is flowing in per unit time. That's the energy we are adding per unit time by the rotor working on the fluid. So this is the power expended. In our case, it's an induced power expended because the excess energy is in the excess induced velocity. So energy flowing out, which is this quantity, minus energy flowing in, which is this quantity. So this V infinity squared term cancels out. 1/2 times 4 becomes 2, m dot. There's a V here, there's a V squared here, so I bring the V here, then you get this expression. Now, 2 times m dot times V is the mass flow rate times the change in the velocity is the thrust. Remember, in this direction, vertical component, we only have V infinity sine alpha t path plane. Here we have V infinity sine alpha t path plane plus 2V. So we have increased the vertical component of velocity by 2V. So the vertical thrust is mass flow rate times the change in the velocity in the vertical direction. So mass flow rate, which is m dot, times 2 times V, so that's the thrust. This is in the square bracket. So this is what we get for the power expended by the rotor. Now, this is ideal power. That means there's no viscosity, there's no profile loss, nothing else. But in reality, we'll have a blade has got a viscous drag, so we have to drag the blade through the air. There'll be some resistance, so we have to supply power to overcome that resistance. That's what we call profile power. We are going to compute it later in this module. Now, if you look at the force balance we did in a couple of modules ago, T times cosine alpha t path plane is vertically pointing upwards. So that's the weight, we're balancing the weight. On the other hand, T times sine alpha t path plane is overcoming the drag. This is the forward directed thrust force. This is the rearward directed drag. So replace T sine alpha t path plane by drag, then this is called the parasite power. So the fuselage drag, landing gear drag, hub drag, even the rotor drag, everything is included, is put in here. But the induced power then just becomes the thrust times the induced velocity at the rotor disc. So this is the induced power. So the only term that is left over is to compute or quantify the profile power. So we do it as follows, very approximately. So we say, okay, this is the road, this is the typical rotor blade, it's spinning round and round and round. At every section of small width delta R, the drag force per unit span, is 1/2 times density times velocity squared. Velocity squared is omega R due to the rotation of the blade plus V infinity times sine of psi. Why is it sine of psi? Because when psi equal to 90 degrees is full V infinity is being added, omega R plus V infinity. When psi is 270 degrees, sine of 270 is -1, so it's omega R minus V infinity. This is on the retreating side. On the other hand, behind the pilot over the tail boom, psi is 0, so we only get omega R. In front of the pilot over the nose of the fuselage, psi is 180 degrees, you just get omega R. So this is the tangential component of velocity. So 1/2 times velocity squared times c times some average CD naught. So we are going to approximately assume that c is chord is a constant, some average value of chord. CD naught is constant, some average value of drag. Then to compute the power, what we have to do is you have to compute the multiply by the force times this velocity. So it will become 1/2 rho velocity cubed times c times CD naught. This is that just one instance in time. So if you want a torque, you multiply by the radius. If you want a power, you multiply by the velocity. So let's take a look at the torque. So this is the drag per unit distance, unit span that we saw up here, per foot of span or foot of radius. If you multiply by the delta R, that you get the actual drag of a small element. If you multiply by R, this is the torque generated by that element. Integrate sum up over all such elements. In your homework number 2 and the quiz, we are doing the summation by numerical integration. Here we are doing analytical integration. This is just at one instance in time. So when you go around the azimuth, you just azimuthally average from 0 to 2 pi, integrate in the d psi, then put 1 over 2 pi. This is just for one blade multiplied by b. So if you do that, you will get a Q naught. Then to non-dimensionalize CQ naught, all you have to do is divided by density by tip speed squared times the disk area A times the rotor radius R. So if you plug in for d prime from here, plug in for ut from here, perform the radial integration, then azimuthal integration. It's just 3 or 4 lines of calculus. Then you get, this is the profile torque that we get. Remember in Howard it was just sigma CD naught over 8. That's all we had. But now we have sigma CD naught over 8 plus 1 plus mu squared. This is the excess component that we get because we are flying in the forward direction. The faster we fly, the higher this number. Although advance ratio is typically between 0.1 and 0.4 for most helicopters. 0.1 means the forward speed is 10% of the tip speed. Tip speed is roughly 600 feet per second. So 0.1 times 600 feet per second is 60 feet per second forward speed. 0.4 means 240 feet per second. That's a very, very fast speed for helicopters. Okay. All right. So this is for the torque coefficient. This is for the actual torque. How about the power? Instead of radius, you multiply by the ut. So plug in the expression for d prime that I showed in here, and then substitute for ut this quantity. Then integrate with respect to radius first, then integrate with respect to azimuth. Then you'll get a power coefficient to be like this. It'll have a 1 plus 3 for power, whereas it'll be 1 plus 1 times mu squared for torque. So CQ is no longer equal to CP in forward flight. CQ 0 simply means like a CD naught is a profile drag. CQ naught is the profile torque. CP naught is the profile power of the blade. So all we have to do is add this profile power to the induced power and the parasite power that we did earlier. Then we are in business. This is the total power consumed by the rotor, even the whole helicopter in forward flight, because the rotor is the sole source of supplying this power. So the first component is induced power. We already saw that induced velocity decreases with forward speed. Remember, lambda I roughly behaves like CT over 2 times mu, where mu is the advance ratio. So the faster you go, smaller the induced velocity. Therefore, for a given thrust, this component steadily decreases as well as forward velocity V infinity increases, or as advance ratio, which is roughly V infinity cosine alpha tip path plane divided by the tip speed increases. Parasite power varies like velocity cubed because it's the drag of the vehicle. This is the drag of the vehicle times forward velocity. There's a V infinity squared here, there's a V infinity squared here, so this can be infinity cubed. This is some reference drag coefficient about some reference area. For airplanes, the reference area is clear cut, it's the wing area, projected area of the wing. But for a helicopter, we don't have a wing, so which area should we use? Should we use rotor disk area A, or should we use the fuselage cross-sectional area or something else? So people could never come to an agreement. So they said, since I cannot determine what should be my reference area for conventional, I'm going to just say CD times S is something called an equivalent flat plate area. Why do we call it? Because if you take a flat plate area, hold it up vertically in air, you'll have a CD of 1. Then the projected area of the flat plate facing the wind is S, would be this quantity F. The power would be 1/2 rho V squared times F. That will be the drag on the flat plate. So we are CD times S, therefore it's called an equivalent flat plate area, as though the rotor is converted into a flat plate of this area. CD is non-dimensional, S has got a units of dimension. So we don't know how to define S, so we define the whole thing from measurements. So we'll measure the drag divided by 1/2 rho V squared. That would be F. Okay, so this would be F. Drag is 1/2 rho V squared times F. Measured drag divided by 1/2 rho V squared, that's F. That's called the equivalent flat plate area. So therefore the parasite power is 1/2 rho V cubed times F. This is the parasite power. So the induced power is going to decrease with the forward velocity. It also will decrease with the advance ratio mu. Mu is V infinity times cosine of alpha tip path plane, which is called the edgewise velocity, divided by omega capital R, which is the tip speed. Parasite power, on the other hand, varies like a velocity cubed. So if you double the velocity, the power is going to go 8 times. Just like a car, if you go from 30 miles per hour to 60 miles per hour, drag varies as 4 because it's proportional to velocity squared. Power varies as 8 because it's a velocity cubed. Okay, so you need lots more power. So how about the profile power? This is Cp naught that we computed earlier times rho A times the tip speeds cubed. So it starts with sigma CD naught over 8 times rho A omega R cubed. That's in hour. But as you go faster and faster, the advance ratio increases. Therefore, this curve increases. Therefore, the power consumption is given by induced power, which decreases with forward velocity, parasite power, which varies as velocity cubed, and the blade profile power, which varies as 1 plus 3 mu squared. If we add up all these 3 components, this is the total power of the helicopter in forward flight. Initially, the power actually decreases compared to hover. So if you're standing still hovering, you're consuming a lot of power, burning a lot of fuel. But if you start moving forward, the power actually decreases until at some point the parasite power rise takes over. Then this curve starts shooting up. Why does it initially decrease? Because the induced power is decreasing. Okay. Now the expression is Cp is Cp induced, Cp parasite, Cp naught. So Cp induced is the induced power, which is thrust times induced velocity divided by rho A omega R cubed. Split this into this component times this component, so it's Ct times lambda I. Parasite power is 1/2 rho V cubed times F. So it's 1/2 rho V cubed F. Cp is divided by rho A tip speed cubed. Then V infinity cubed by tip speed cubed is approximately advance ratio cubed. Not exactly, because it should be V infinity times cosine alpha tip path plane. But since alpha tip path plane is a very small number, cosine alpha tip path plane is close to 1. Therefore, the forward speed by tip speed is roughly the advance ratio. F over A, equivalent flat plate area divided by the disk area, is the parasite power. We already showed earlier, not later, this is the Cp naught. So if we add it, this is the power consumed by a helicopter in forward flight. All this power is being added to the airstream by the rotor. That's why we looked at the rotor, what happened at the rotor disk, then we were able to develop this expression. This expression is approximate because it assumes the inflow is uniform. We know it's not uniform. It also assumed the CD naught is a constant. We know it's not a constant. When shock wave forms, you're going to have a very high drag because of the wave drag. Therefore, this relationship is usually empirically corrected. Therefore, we use some empirically corrected formula for non-uniform losses, swirl losses, tip losses. to compensate for the fact we are using an average drag coefficient. So what is done in common practice is kind of correct this expression that we just derived rigorously by adding a kappa correction factor for the induced velocity. This is a 15% more. This extra 15% is for the swirl effects, for the tip loss effects, and any other induced inflow, incorrections, non-uniform inflow, those type of an effect. And this 3 has been bumped up to 4.6 because when the shock forms are at high advance ratio, CD0 is going to rise very dramatically. So it's no longer a constant. So this is what is used in the vehicle performance that we will see later on. Again, revisit this equation in our course. So plotting these three curves, so induced power, parasite power varies as velocity cubed, blade power, profile power varies as 1 plus 4.6 mu squared. So this component is the profile power, parasite power, induced power. Then this is the available power. So you have excess power. So the excess power is what you have to climb vertically up or down or gain altitude. So when the vehicle is trying to gain altitude, like a helicopter from low altitude to high altitude, it's this excess power divided by the weight of the vehicle is the rate of vertical climb. So you could estimate the vertical climb rate from this excess power divided by the vehicle weight. Where do we have the extremely excess power? Right here. So when you go in here, you have the largest amount of excess power, so you can climb the most rapidly in the vertical direction at this forward velocity. At some forward velocity, your available power equals your required power, which is this purple line. So you cannot fly any faster than that. So this is your maximum forward velocity. This is your hover power. This is your maximum forward velocity power. This is the power at any intermediate velocity. So we have concluded our section on power consumption of a rotor, for that matter of the helicopter itself, because the parasite power is included in forward flight in this particular video.